Alright, welcome back everybody. In this video we're going to look at the examples from the limit comparison lesson. And limit comparison is a lot more powerful for us than direct comparison because we don't need to worry about whether or not the function is slightly bigger or slightly smaller that we compare it to. All we need to do is find a function that we can take the limit of this, and usually we pick a function to force the limit to be a finite value. And if we do that, if we can find another function that when we take the limit of our original function and the other function, it ends up being a finite value, that means that the two functions share convergence or divergence behavior. Okay, so that enables us to kind of cut through the idea of is it bigger or smaller and just kind of compare. So I'm looking at this function. Basically, I know that the numerator is going to get be somewhere between 0 and 1 based off of the limits of integration. And so what I end up doing is I'm just going to compare this to 1 over x. And then I take the limit of the ratio of these two as x approaches infinity. And so I take the limit of the ratio of these two functions as x approaches infinity. And that's equal to the limit as x approaches infinity of, and with some simplification, ends up being that. And that limit is 1. So, integral from 1 to infinity of 1 minus e to the negative x over x, and the integral from 1 to infinity. Same limits of integration share convergence behavior. Since the integral from 1 to infinity of 1 over x dx diverges, because it's a p integral with p less than or equal to 1, the integral from 1 to infinity of 1 minus e to the negative x over x dx also diverges by the limit comparison test. Alright, not bad on that one. Let's go on to the next one. Does this integral converge or diverge? What would be a good thing to compare it to? I'm going to compare it to the square root of x. Accordingly, 1 over the square root of x. And so I've got the limit as x goes to infinity of 1 over square root of x plus 1 over 1 over square root of x. It's equal to the limit as x goes to infinity of square root of x over the square root of x plus 1, which is the limit as x goes to infinity of the square root of x over x plus 1. And since what's inside that square root approaches 1, the actual limit equals 1. So I've shown that these two share convergence or divergence behavior. So, integral from 2 to infinity of 1 over square root of x plus 1, and integral from 2 to infinity of 1 over the square root of x share convergence behavior. Integral from 2 to infinity of 1 over square root of x dx diverges because it's a p integral. with p less than or equal to 1. So the integral from 2 to infinity of 1 over square root of x plus 1 diverges by limit comparison. Alright, move on to example 3. Does this integral converge or diverge? Compare it to 1 over x cubed. So the limit as x goes to infinity of 1 over x cubed plus x over 1 over x cubed. That's equal to the limit as x goes to infinity of x cubed over x cubed plus x. And if you can't see that this limit is 1, apply L'Hopital's rule a few times, and you'll see that very quickly. So, integral from 3 to infinity of 1 over x cubed plus x, and integral from 3 to infinity of 1 over x cubed. Share convergence behavior. Integral from 3 to infinity of 1 over x cubed dx converges because it is a p integral with p greater than 1. So, integral from 3 to infinity of 1 over x cubed plus x converges by direct comparison. Okay. Or pardon me, by limit comparison. Right, so you notice in those first 3 examples how important that property was with p integrals and when they converge and diverge. And that's one of the reasons why we emphasize that, is because it comes in enormously handy when we're doing limit comparison. Anything that we can compare to a p series works well for us. Now, example 4 here is a cautionary tale. A lot of people, their first instinct on this might be to attempt to do a comparison to a p integral. Unfortunately here, there's a couple problems with that. The first problem is the fact that the x is negative inside of the radical. That's one problem. The other problem that lies in doing a comparison to a p integral is that all the p integrals are based off of the lower limit of integration being some value greater than 0, which is not the case here. And this illustrates the point for us that in spite of the fact that we have direct comparison and limit comparison to use, they are not always the best way to determine if an integral converges or diverges. Sometimes the best approach is still just integrating this. And so we look at this function, and it has an infinite discontinuity at 4. So in order to integrate this, I'm going to find the limit as x approaches 4 from the left, the integral from 0 to 4 of 1 over square root of 4 minus x dx. Wow. Sorry, my brain like imploded there for a moment. We want the limit as b approaches 4 from the left, or the integral from 0 to b. And now we're just going to go ahead and integrate this. And the integral of this is going to be negative 2 times the square root of 4 minus x, evaluated from 0 to b. And that's going to be the limit as b approaches 4 from the left of negative 2 square root of 4 minus b minus negative 2 square root of 4. And if we simplify this further, the limit as b approaches 4 from the left of this term is going to just be 0. And so the value of this limit is 4. Therefore, this converges. Okay? So at this point in time, we have 3 real decent ways to figure out if an integral converges or diverges. We can either use direct comparison, or we can use limit comparison, or we can just go ahead and take the integral if it's an integral that we can find by basic integration techniques. Alright, that's the end of this video and the end of this unit. Yay! Hope you enjoyed it and have a great rest of your day.